Wireshark analysis of a very complex file. This capture file is dated from the 11th of the 11th 2008. There's an awful lot of data inside this capture file. We need to work out how and what we can find inside here. We're not exactly sure what we're going to see. If I scroll down to a random point and select a frame, I find TCP on port 445. So I know there's Windows disk shares. If I skip to another random frame, TCP directed to HTTP, FINAC. So this is teardown of web traffic. This is a very inefficient way of working. So what I'm going to do now, I'm just going to do some statistics, and I'm going to look at endpoints. Who am I talking to? We should have a little graph in a moment. Here we are. We know that everything is running over Ethernet. We can see several Ethernet adapter types and full serial numbers. So these are UI, the Organizational Unique Identifier, and then the serial number. We can see 3COM, Azustec, 3COM, Gigabyte, spanning tree for bridges, IP4 multicast, and broadcast frames. Let's have a look at IP version 4. We now know that we're running IP on top of our network. 172.32.51.1 has done a great deal of data transfer across the network. Okay, it's received a lot of bytes, it's transferred a lot of bytes. It's a top talker. That's something that we want to investigate. 253.100 has done a lot of frames. If we go from the top of the tree and then work our way down, we're going to hit a large amount of frames, and therefore we're going to find out what's happening at any given point in time. So we do need to work on that. If we look at TCP, we're now looking at the TCP protocols and potentially the port numbers. Here you can see all of the ports, so we've reordered everything in port terms. Okay. And again we can find out how many frames there are there. We can also look at UDP. In effect, we're seeing router ports, domain ports, bootp server, bootp client. So we know there's DHCP and DNS on the network. Okay, I found out some information here. Now I actually want to put it into practice. I'm going to filter all of these frames by the protocol field, and I'm going to scroll right to the top. First protocol, UDP, 300 bytes on port TCP MUX, port 1. Binary data down the bottom here is fixed. That doesn't look standard. Let's look at the next frame, TCP. TCP port 80. So we can see that we've got some sort of like web traffic going on here. Move down. We have oodles of TCP, and then we're into something specialist. We can see SMB, the server message block, part of Windows. So we can analyze what's happening inside that by going down here. Read and X request. So we're reading, or we're sending commands to Windows to attempt to read a directory tree or something. The received frame, the next frame. These are very complex protocols to actually extract any information from. Maybe easier to do that later. We've got SMB. NBSS, NetBIOS Session Service, continuation data. This is where we're looking at information that's coming from Microsoft DS, the domain server, on port 445 TCP, to a random high numbered port. Okay, we can see IGMP. IGMP, Internet Group Management Protocol. So something is trying to actually work out how it can manage in this network, or manage part of the network. It's wanting many people to join in. The address that's used is 224.0.0.22. That's a Class D network. We can see there's a great deal of pings activity on the network. 9 bytes of payload. That's unusual. Look at that. Rickety. So the payload here is a custom payload. The payload is rickety, so that doesn't necessarily look like a normal ping. Time to live 64. It's come from Linux. It's under control. Payload is under control. Logical guess, it's some sort of spoofed frame, but spoofed frame correctly, therefore we will have a response. Okay, these are all the same, and we have HTML gets. Down the bottom here we've got DHCP. Right, there are too many frames to try and filter. So what I'm going to do, I'm going to look for key frames. I'm going to find out what the IP addresses are on this network. Boot P C, or boot P as a display filter applied has now shown me here we have Ethernet frames, we have IP frames, boot protocol server. We are being relayed and we're looking for information. Expand these up like we've done before. You can clearly see inside here we're looking for subnet, router, domain name, broadcast, static routes. Okay, that was the request. Let's have a look at the acknowledgement. The acknowledgement has filled in all those frames. Let's have a look at the detail. Server is 172.32.51. Lease time is 5 minutes. Subnet mask /24 bits. Old style Class C. Router address is 253.254. That's the highest address in the subnet. Domain name. Okay. Domain name servers are 172.30.251, 192.168.250.10. The actual name for this network, wireless.ric. Wireless.ric. Okay. We have many more acknowledgements and requests for different systems. Here we can see a request for a machine on 157. This machine seems to be identifying itself in the Microsoft class version 5. It's Win2K style of networking, and the following frame actually provides us with further information on that system. Okay. We don't appear to have any more complex DHCP requests, renewals or whatever, but at least we found out a little bit of information about our network. We can see that our DHCP server is in one subnet and our clients in house wireless or in wireless.ric are in a different network. Let's clear that and let's have a look at some DNS frames. Let's see if we can find any domain name service frames. We've found quite a lot. cs4clearspring.com, youtube.com. We're finding a great deal of information here in our network that can be of use to us. These will be of use because we know that they're trying to talk out, possibly using some sort of web page. A query to www.kylie.com, for example. Let's take this as an example. 172.30.251, destination 208.67.220.220. That's a global IP address, and that's the local IP address. So Where is that going to? What address is 208.67.220.220? Let's go and ask our friend Google. Okay, I'm going to put this address into here, 208.67.222.222. I'm just putting the IP address directly into Google. Let's see what comes back. As if by magic, we found out that that IP address is part of the Open DNS servers. So in effect, inside this network we have a DNS server that talks to the Open DNS servers for information. What I'm going to do now, I know that this is frame 6649, I'm going to clear the filter, and as you see I'm at 6649, this DNS frame. I have a response from that frame. Let's have a look at the DNS results that we got for that particular query. Okay, our query was to www.kylie.com. Our response was that Kylie.com is a CNAME, that stands for Canonical Name Form, and it's named to Kylie.com. Kylie.com then resolves to the IP address 195.225.83.33. So we now have the address. This frame here is a HTTP frame that followed those DNS frames. Logic might suggest that that's actually going to the Kylie address, especially when you look at the IP number 195.225. So I'm going to do a follow TCP stream. In following the stream, I leak information. So let's see what I have leaked. What platform am I sat on? Ubuntu 8.04, Firefox 3.03. You now know that I am running Firefox and I'm on the Ubuntu type of system. You can clearly see identified Linux 686 type of core. If we look at what came back from the servers for Kylie, they were reusing the Apache as the Apache web server, X powered by PHP 439. Notice there's no banners, or there's no enumeration banner telling you what type of Apache server, so they're not leaking too much information from their servers so that people can try and attack them. We also see that we're setting cookies which will be set on our client, which would then uniquely identify us so that we can come back again. What follows here is lots and lots of HTML with some client-side scripting, some JavaScript, looking at the cookies. So that's quite a little bit of information there. We know that we have told the web server more than we have going back from it. I have cleared the filters again, and now what I'm going to do, I'm going to look for something else inside this frame. I want to know if we've got any secure shell traffic. SSH. Apparently not. SSH will be on TCP port 22. It's not seen in here. Let's have a look for some Telnet traffic. Telnet traffic is on TCP port 23. Apparently not. Let's have a look for some server message block traffic, some Windows disk shares. We have found quite a few frames here. Let's see if we can filter and extract some further data. We're going to do a follow TCP stream. Now this is actually very complicated to try and get any kind of useful information out of it. As you can see here, we've basically got binary data, or something that represents binary data, in our response from this filter. Let's just scroll down and see if anything jumps out and is obvious to us. so far, nothing is particularly obvious. Okay, it appears that we can't capture any useful information out of what we've just seen. All we know is that we're exchanging data, and it appears to be quite a considerable amount of data. We can't see any file names or passwords or listings of directory trees, which we would often see inside this type of traffic. It's almost a little bit random to determine if you can see that or not. Let's have a look at some more complexities that we can see inside this network. We know from looking at some of the protocols that there's some other types of traffic inside here. So let's see what recalling what they were. Let's have a look. STP, Spanning Tree Protocol. All of these frames look exactly the same. All of these frames are the same. Let's take one apart and have a look at what's inside it. A spanning tree frame is an Ethernet 802.3 frame. It is not an Ethernet 2 frame. The type length field is 39 bytes, which means it is a small frame. It also means it's Ethernet 2.3, not an Ethernet 802.3 frame. On top of an 802.3 frame we have an LLC header. This is a logical link control header. As you can see in here, all the numbers are set to the standard values. The destination service access point and the source service access point are set to 42 hex. On top of the LLC header and the 802.3 header, we have spanning tree. Let's have a look at the details inside spanning tree. We have something called BPDU, Bridge Protocol Data Units, and BPDU flags. These are saying this is a proposal, port role, learning, forwarding, agreement. The flags are set to yes. Topology change acknowledgement is set to no. Topology change is set to no. Therefore, the network, the switch network, hasn't had a new switch added to it. If it has, it will become a topology change notification and the frames would change. The root identifier says this person is the root bridge. The path cost to get to the root bridge is 0. That means this particular switch is the root bridge. The most likely scenario for that is we only have one switch. If we look at the details, the max age timer is set to 20 seconds, hello timer 2 seconds, forwarding delay 15 seconds. We now know several things. If you look up your spanning tree protocol, we'll find out that this is standard 802.1d, basic spanning tree. So we found out something useful here. We know that we are connected to a managed switch. We can see from this header that it is a 3COM UI. This infers that we are connected to a managed switch that is 3COM. We've seen some switching information. Let's see if there's any routing information. Let's have a look for RIP.